it's time to talk about the chain rule. So far, we've talked about derivatives, products of functions, quotients of functions, differences, sums, but we've been pretty limited in our scope of what kinds of functions we can take derivatives of, because we need the chain rule to go much further. So what we're going to consider are functions composed. Composition of functions. We want to take derivatives of things like e to the sine of x squared plus 1. I want to be able to take the derivative of that function. So how do we do it? What's the chain rule say? Well, the chain rule says that I review this as a composition of functions, and I take the derivative of the products of those derivatives. The derivative is the product of those derivatives independently, respecting composition. I think the right way to show you is to do it by example. So there's like an inside-out perspective, and there's like an outside-in perspective. I'm going to do it in one way or another today. So I'm going to do it in the outside-in way. So I'm going to look at the outsidemost function. What's the outsidemost function? What's the outsidemost function? Is it x squared plus 1 or e to the outermost function? What's the last thing we're doing? It's the e to the function is the very last thing that we're going to do. So this thing looks like e to the something, and how about I call that g, where g is equal to sine of x squared plus 1. Okay? And we're going to need to then keep going on this thing and realize that this is the composition of some things. So that's the same thing as sine of h, where h is equal to x squared plus 1. Right? So I've got f is equal to e to the sine x squared plus 1. G is sine squared plus 1, so the next level in. And then finally, the innermost function is h in this case. So the nesting is 3 deep. Right? So if you were to compose back in these functions, you would get back the original f. So it starts out that f is equal to f of x, but it's also equal to f of g, and g is equal to g of h, and h is equal to h of x. So we've got this chain of functions, right? And they're like chained together. At the top level, I've got f is f of x, right? And once you've walked your way down the chain from outside in, you get back your original function, right? Because you would take like h of x, substitute it for h, take that and substitute it for g, and you get the original thing back, right? Take this x squared plus 1, put it in for h, take sine of x squared plus 1, put it in for g, and then you have e to the sine of x squared plus 1, which is your original function. Okay, so I've got these functions right here. Let me go ahead and align them back up. So f is e to the g. Oh, I smeared it. G is sine of h, and h is x squared plus 1. H is x squared plus 1. So for each of these functions that we're considering right here, we're going to let that thing be the variable, right? That thing's the variable. This thing is the variable. So we're going to take the derivative with respect to that thing. So I'm going to write df dg and take the derivative with respect to g and get e to the g. Okay, because the derivative of e to the is e to the derivative of g with respect to h is, let's see, the derivative of sine is cosine h. Right? I'm gonna be really specific about what thing I put inside of here, because then I'm gonna like compose them all together to get the original thing. And then finally, I'm gonna take dh dx, and that's gonna be 2x. Okay, so I have my original functions. I have this list of derivatives, and we're trying to compute the derivative df dx. This is my original function right here, and I want to take its derivative, but we don't know how to take the derivative of this thing yet, right? I know how to take the derivative of basic building blocks of functions, e to the x, sine of x, x squared plus 1, but when they're all composed like this, the chain rule is in effect. We have to use the chain rule to do this. So df dx is equal to the product of these derivatives, df dg, dg, dh, dh, dx. And those are all multiplied together. I'm not going to put the dot in there to indicate the multiplication. So I'm going to go e to the g times cosine of h times 2x. But we're not quite done, because now I'm going to invoke the definitions of what my functions are to put them back into place. So that's equal to e to the g. Well, g is sine of h. So e to the sine of h, but h is x squared plus 1. So that's this part. The cosine of h, but h is still 2x plus 1. And then finally times 2x. And that's our derivative. I see no available simplification to this function. And this is kind of a fairly typical modest difficulty chain rule function. Of course, we can make these things arbitrarily complex by just putting a bunch of crazy pieces together. But figured we'd start reasonable. So, right, I've got this original function right here, and I recognize it's not just a basic function. It's not just e to the x. I've got some more complicated thing going on. And so I'm going to like pull on that chain and take the product of each thing as I like pull them outside. So at the first level I have e to the. Here's the derivative of e to the. At the next level I have sine. Here's the derivative of sine is cosine. At the next level I have x squared plus 1. And here's the derivative of that, 2x. And always I'm taking another link off the chain as I take these derivatives and work my way into the thing. So that was the outside-in perspective. I think I'd like to repeat that one more time doing the inside-out perspective. I'm going to do less gory detail as far as this goes. And in fact, I think I'm going to wipe the whole thing over. So we're still going to take the product of each of those things. I'm going to move a bit faster in this next part. But I'm going to get the same thing. And it shouldn't matter whether you take the inside-out or outside-in perspective. I find that people typically find one or the other easier. So the only way to know is to just like try doing derivatives. And don't wait for me to make up problems. I just made this problem up. And you absolutely are empowered to make problems like this up too. Nothing is stopping you from just making up your own functions and taking their derivatives. In fact, maybe that's what you should be doing. I'm going to try adjusting the light 1 bar. We'll see how this goes. Hopefully that didn't make it too dark. All right. So this was the outside-in perspective. I looked at the outside-in. Let's do inside-out. So I'm going to go and inspect my function and be like, what's the innermost function in this thing right here? And I see it's x squared plus 1. So if that's f, then f prime is going to be equal to, I'm going to take the derivative of that x squared part right there, and I'm going to have 2x. Now I'm going to go out a level. Now we've got sine of x squared plus, how are my hands doing? Sine of x squared plus 1. Well, it's just a sine, it's just sine, because we already dealt with the inside part. We only have to deal with one level at a time as we pull our functions out on this chain. Derivative of sine is cosine. Cosine of x, oh, there's that problem. You will make that you will make that mistake. I started writing on the derivative of the inside there. No, but the inside is modified. We already dealt with it. X squared plus 1. And then on the next level, so I dealt with the sine part. On the next level, I have an exponential. The derivative of e to the is e to the, you have to chain the thing out, times e to the sine of x squared plus 1. And if you check, these are exactly the same function. I just wrote them in different orders because I chained from inside out or outside in. It doesn't matter which one you do. Just choose one and maybe get good at it. Sometimes it'll feel more natural than others. But that's the chain rule. You take the products of your derivatives one layer at a time, and you'll get there. Thank you so much for watching, and I'll catch you later. Bye.